we are going to start with thyristors and phase control rectifiers. Though we have stopped the triple fired monostable and we still have to finish the digital logic design, the remaining part, we are starting with this topic because next practicals will be based on this. So I'm trying to match the theory and practical. In that case, sometimes I have to go back and forward again. So let's start this. You know something about diode, I guess, from the first year. So I will also start my writing pad. Yeah, it's paint. Uh, and let me take some thick. So basically, diode is a PN junction device, and it allows current flow only in one direction. Uh, Now, you might have also studied somewhere something called as transistor, which could be PNP or NPN. And basically, the symbol for transistor is like this. So it allows us to transfer the resistor, whereas diode allows only one directional current flow. Now we are going to learn something called as SCR or silicon control rectifier, which is a combination of P and PN, like two diodes connected in series, but it also has one extra terminal, which is a gate. So you can imagine a three-dimensional structure might look something like this: a cathode, then there is a small portion of it, then there will be a anode nor p type, then n minus p and n cathode. So this is how a silicon controlled rectifier looks like. Now, as the name says, it's silicon. So it is made up of silicon, either p type or n type silicon, and then something called as controlled rectifier. Maybe in first year you might have studied about a rectifier. Now, a rectifier is a circuit that translate any AC waveform into a DC waveform. So if you remember, a rectifier is defined as something that converts this kind of wave into a DC, which doesn't change with respect to time. So AC to DC is what we call a rectifier. And then what we have is this term called silicon controlled rectifier. And the controlled rectifier part we will study it later. But uh, if you go on a broad side, uh, this is the equivalent to transistor analogy of SCR. So you have firstly PN junction. I will also take my pencil. So if you look it closely, you will see there is a PNP transistor and then there is a NPN transistor. So I can just split them for my convenience like this: T1 transistor PNP and then T2 transistor. Then that becomes my first terminal, second terminal, third terminal for first transistor, and first, second, and third terminal for the second transistor. And there is one more extra terminal gate which is connected at this emitter of PNP transistor. Now, a property of a transistor is such that when you apply a pulse, a positive pulse to an NPN transistor, this thing turns off. That is, it goes from its cutoff mode to saturation mode. So you can imagine a transistor as an electrical switch, which get turns on if you give a pulse. The major advantage of this transfer of resistance is this pulse has low current capacity, like few microamperes, and still this current is a high current capacity, like in milliamperes. Typically, the ratio is 200, what we call current gain of a transistor. So whatever number you have at the base, that gets multiplied by 200. And that's why this is also known as current amplification device. So it amplifies the current. What does this help us here? Like NPN transistor triggered on the positive pulse, whereas PNP transistor get triggers with the negative pulse. Now PNP, the arrow goes towards the base, and this transistor gets turned on when you give 5 volt to 0 volt pulse. So now Initially, both transistors are in off state. As soon as you apply a pulse over here, what we call a gate pulse, what will happen? This transistor gets turned on. Because of this transistor getting turned on, the T1 will receive a negative voltage from this point. As soon as it gets a negative voltage from this side, this transistor get turned on because it's PNP, and that will provide a positive voltage to NPN. So now if I remove my gate current, this transistor will remain on, and that's why you can control the operation of this device from anode to cathode. So this becomes your SCR. Now physically they are not made like this. This is just a two transistor analogy, but physically they are made like this. And by just applying a gate pulse, it goes and latch itself into on mode until and unless one of the transistor comes to the halt, which we call commutating the SCR. So what we say in the language कि उसको trigger मार बाद में वो खुद ही कर देगा काम. SCR भी वैसे ही है. SCR को you give a gate pulse and then it will start from so it goes to on state and remain there. So that's the use of the controlled rectification. So now you can have current flow from anode to cathode, but when we apply a gate pulse, there is still no reverse current flow because of this PNPN structure. The current cannot flow from cathode to anode. So it's a unidirectional. You can say it's a diode, but it's a diode that can turn off whenever you want. So there is an extra symbol. So the symbol is very similar to a diode, but with extra terminal of gate. So this is how SCR works. This is another diagram where the same thing is shown, the two transistor analogy. And finally, the characteristics of SCR compared to your regular diode. So your diode has this characteristic where this voltage, what we call knee voltage, could be 0.3 volts or 0.6 volts, and sometimes you also call it 0.7 volt. So these two readings are for silicon and this one for germanium. So the reverse bias characteristics are still the same for the SCR. There is a reverse leakage current because of the minority carriers in the transistor. Then there is a breakdown voltage after which device breaks down and it starts conducting. There is a positive current, but this time there is something called as forward breakover, and then if you look at it closely, then it's clear diode characteristics. But this device will not start conducting either till you apply a gate pulse, like you have three gate pulses here. The lower the magnitude of the gate pulse, faster is the triggering, and also if it reaches the VBO, it will also start into the conduction mode. So basically you can imagine SCR is the switch. उसको अगर गेट पे आप पल्स दोगे तो वो चालू हो जाएगा, otherwise it will remain off. Now there is something called as UJT, which is unijunction transistor, and this UJT basically provides a gate pulse to the SCR. अब यूनी जंक्शन मतलब इसमें एक ही जंक्शन है, तो इफ यू लुक एट इट केयरफुली, UJT is like a PN junction diode with P type, which is typically anode, is what we call emitter, and then there is a large cathode, but which is divided into two terminals, base 1 and base 2. So if you see a equivalent circuit of a UJT, it's a diode with two resistance, RB1 and RB2, and you can control this by the special characteristics called negative resistance region. So there is a concept called negative resistance that says when you apply or increase a positive voltage, then your current decreases. So that means the resistance should be negative, uh, which is just a term. Physically, no resistance can be negative, but because we are increasing the current voltage, but because of the special nature of the UJT, the current is decreasing. So that's why we call it a negative resistance region. And this is how the characteristics of a typical UJT looks like. So if you start increasing the voltage, what will happen is it will go up to the peak point, it will increase during that point, and then suddenly it hits this negative resistance region where your voltage is still increasing, but current is now decreasing because your diode has gone from off state to on state. So as your diode has gone off state to on state, there will be a current. So initially, you can imagine there is no current coming from this side, and suddenly when this diode turns on, the current gets added, and that's why the actual value of current, which is in this direction, is reducing because of this excess current, and that's why your overall current is reducing, and that's why you reach till valley point. Since it has compensated for all the excess electrons, now you will again have your regular current increasing. So that is where your saturation is reached or UJT got turned on. And if you see the circuit diagram, there is a capacitor always connected at the emitter junction of the UJT, which gets charged till a point where this diode gets turned on. As soon as diode gets turned on, it will get a discharge path through this R1, and then till a point, as soon as it reaches a point where this diode will automatically get turned off, again the capacitor will start. So this circuit, even though you have applied a DC voltage, it is automatically turning on and turning off. And what happens to the voltage, since it was off, it will have a very high voltage here. Suddenly when it gets turned on, it will have a very low voltage, and slowly it will increase. Again it will reach to its maximum, and since at that point it remains there, as soon as again this capacitor turns on the device, the voltage drop across this will go low. And similarly, as soon as the device get turned on, suddenly all the voltage drop will appear across R1. Then it will go on decreasing because of the decay in the capacitor charge. Because capacitor starts discharging, the voltage starts going away. As soon as it gets turned off, again it will build a high voltage, and again it will start discharging. So you get a positive pulses which are used for triggering SCR at the base, and the value of this charging and discharging is controlled by this resistor R3. So this is how a complete circuit looks like, SCR triggering circuit. You have a switch to turn on the circuit. Then this is a UJT relaxation oscillator. Then through a current limiting resistance R4, it is connected to the gate of the SCR, and this is your actual load. So if you see the voltage across capacitor, it is charging, discharging, charging, discharging, and the ratio of RB1 and RB2, that is internal resistance of these two devices. So you can imagine there are two resistors connected to a diode in a UJT. So if you want to turn on this diode, you have to overcome this voltage which is at the cathode, and this voltage Vk, I guess in earlier lectures also we have seen, given by a voltage divider bias of R1 and R2. So basically, if you control your R1 and R2, you can control Vk, and that will inherently control your diode turning on and turning off voltage. So the intrinsic standoff ratio, which is internal resistance R1 upon R1 plus R2, is actually controlling this peak point and valley point for the UJT. Now coming to the controlled rectification action, what I would suggest is, first you know everything about the sinusoid. We already know from the first year triple E subject, I guess. There are peak voltages. I typically get confused with RMS and average voltage. RMS is root mean square. So if you square a term, okay, then you take a mean of the different terms, and then you take a square root, then it reaches to this RMS value. Whereas average value is simply averaging out the terms. So that is the difference between the two terms. This is RMS, stands for root mean square. इसमें फायदा ये होता है, since you square, even if you have negative voltage, it will get converted to positive. So negative and positive both terms get converted to positive because of the square, and then you add, if you add the two positive terms, then your overall, this could be a representation of your power. So that's why RMS values are typically important than average values, because average value could be zero also, but need not be for a particular sine wave. So in a sine wave, if you try to find its equivalent DC, then you will end up at 0.63 into a max, which is the maximum amplitude of a signal. Now we also know this angle where peak reaches is 90°, and this is a phase angle of 180° when your sine wave actually converts from zero to back to zero. Then there is 270 where it reaches negative a max, and then finally 360, which is again your complete cycle. So this becomes your period T, and which is nothing but 1 by f. So knowing all this concept of a sinusoid, we will go to the topic called rectification. Now we will slowly go into the control rectification, but we will start maybe in today's practical. We are going to perform this kind of experiments where you connect a AC supply and connect a diode in series with it, and you will find that only positive half cycle will get passed through, negative half cycle will drop across diode. Next, so this is what we called half wave rectifier. Next thing is, obviously there is some mathematics involved behind the half wave rectifier. So you have some average value, then a zero, then some average value, then a zero. So overall, your total average value with half wave rectifier is 0.318 times a max or amplitude max. Now, what will happen if you uh, convert it to full wave rectifier? So as per the theory, there are two kinds of full wave rectifier. A full wave rectifier which has a center tap and both diodes are looking in the same direction, or it could be a bridge type, like you might have studied a diamond shaped bridge earlier, but it becomes very difficult to remember the directions. So to simplify this, always draw a rectifier where all the elements are looking towards God or towards top of the screen. So each and every element is always looking towards top. So you can see this diode, everyone is pointing towards top. And then you connect your main source at the center, and then you try to measure the output across the resistor RL, and you should get your circuit output, that is AC output at that particular point. So what will happen during the positive half cycle? So diode D1 will be forward bias, so current will go through D1, but D3 will be reverse bias, so current will not flow through this, current will go through a resistor. ठीक है, क्योंकि यहाँ एनोड पे let me just clear the drawings to make it visible for you. It is all in constant. Okay. So during positive half cycle, what will happen is this point is positive compared to this point. That is what we call the positive cycle. Let's mark this point as A, this point as B. Now D1 के लिए क्या है? A का वोल्टेज ज्यादा है, पॉजिटिव है, B का नेगेटिव है. तो D1 एनोड पॉजिटिव वोल्टेज है, इसलिए कंडक्ट करेगा. Whereas D3 के लिए यहाँ पे पॉजिटिव वोल्टेज आ गया क्योंकि D1 कंडक्शन में है, तो पॉजिटिव वोल्टेज यहाँ आ गया, और एनोड पे नेगेटिव वोल्टेज है, तो D3 कंडक्ट नहीं करेगा, इसलिए करंट आएगा आगे से, RL के थ्रू करंट फ्लो होगा. Again, when it reaches here, there is a positive sign, negative sign, so D4 will conduct and D2 will not conduct because there is positive on this side, and now there is positive on this side, but diode itself will have a drop of 0.7, so this diode will not conduct. So ये दो diode conduction में नहीं है during positive half cycle, and you will get output because of D1 and D4. Similarly, during a negative half cycle, what will happen? आपका D3 और D2 कंडक्शन में जाएगा और D1 D4 कंडक्शन में नहीं होंगे. So this is how the output waveform looks like. For every negative or positive cycle, you will always have a positive cycle. And if you try to calculate the average value now, it will be same as earlier, 0.637 times Amax, because for every cycle you have a DC corresponding output. So that's why you will have 0.63 times the Vmax is your average value, average output, or VDC, what we call. And then comes the controlled rectification. So this is the experiment that we are going to perform today, a controlled rectification using SCR, where you apply a AC supply. आपके प्रोटियस में V sin शायद होगा term. So you search for sinusoid generator from the components, you apply it, or you can apply a sinusoid, then a transformer, then another secondary of the transformer, and then rectifier. It's okay because transformer क्या काम करता है? Isolating 230 volts from the rest of the circuit. Now we are in the simulation, so we will not receive a shock from 230 volts, and that's why transformer is not needed in this case. But if you want, you can put transformer. It won't make any difference to the circuit as such. Now we connect, instead of regular diode, connect SCRs. Now this is a half control because only two of the diodes are replaced by the SCR. And now what will happen? This SCR only conducts if it receives a IG pulse. Okay, and that's why your entire output cycle is now controlled by the SCR turning on pulse. So if you give a pulse at this location, SCR will get turned off, and because of SCR1 and diode D2, this pulse will complete its half cycle. Then natural commutation to the SCR will happen in the negative half cycle. Again, we wait for the second pulse at SCR. Let's say if you don't give a pulse, then this entire waveform will not appear at the output. It will go to the next waveform. So now you can control the output by controlling the pulse, but obviously you can only control between 0.63 times Vmax to 0. So you cannot increase the output, but you can control between these two levels. So let's say if you want to have a controllable output around 10 volts, then you have to make sure that 0.63 times Vmax is greater than 10 volt. And why the name half control? Because we are not replacing both the diodes by SCR, but just one diode by the SCR. Here is a fully controlled full wave rectifier, where you convert your AC waveform into DC. But this time, typically these two gates are shorted and then applied a pulse to them. Because अगर इसको pulse दोगे और इसको नहीं दोगे तो conduction होगा नहीं, क्योंकि path तो ऐसे ही complete होता है. So that's why using two thyristors. अभी एक डायोड एक थैरिस्टर में मेजर प्रॉब्लम ये था कि डायोड बेचारा लो वोल्टेजेस पे और लो करंट्स पे काम करता है, whereas the SCR can work on high voltage and high current. We are going to see one small video about this, but the basic principle is if you use both SCRs, then your current handling capacity increases. Also, you can separately control these two pulses, and you can have a precise control over your output waveform. So that's why you can go for always full control full wave rectifier. ऐसे भी प्रोटियस में अपने को कंपोनेंट की कॉस्ट तो लगने नहीं वाली, तो you can use both SCRs in your examination or even during your experiment simulation. And at the same time, to measuring this, you can use either probe or a grounded and a CRO to see the output waveforms. And finally, the other two terminals are pulse together, so you can have all full pulse together. But remember, here if I don't pulse on the right time, then your SCR will not conduct. So for example, if this is your waveform, and if you pulse your SCR here, okay, this is the input waveform, this is the pulse to SCR1. Now, since you are pulsing it into the negative cycle, your actual anode positive and cathode negative condition has gone. And now in that case, if you pulse, it will not turn on. तो SCR चालू करने के लिए मेन चीज होनी है, पहले तो एनोड को पॉजिटिव वोल्टेज होना है, कैथोड को नेगेटिव वोल्टेज होना है, और उसके बाद ही अगर आप पल्स अप्लाई करोगे ड्यूरिंग दिस कंडीशन सेटिस्फाइड, then only your SCR get turned off. So this pulsing frequency should be always equal to or greater than your input frequency, which is typically 50 hertz, because you always work with your Indian sockets, or 60 hertz if you go to US and try to do a similar kind of experiment. So typically 50 hertz or more should be your pulsing frequency. Now what will happen if your SCR is already turned on and you apply one more pulse? So the answer to that is nothing will happen because SCR is already on. और ऑन चीजों को और कितना ऑन करोगे, ऑलरेडी करंट फ्लो हो रहा है उसमें से. एंड वी विल ट्राई टू अंडरस्टैंड दिस एंटायर थिंग विद द हेल्प ऑफ एनिमेशन. आई गेस I will stop sharing now, and I will share one animation with you with audio, and we will see this action in detail. So I will also stop recording.